Standards are definitely a good way for kind of bringing security to the masses, to addressing a lot of those developers that need to do secure coding but don't necessarily have security expertise to do so. So I'm definitely going to be interested in seeing what we're going to be talking about here. Welcome.
I think I might need a mic. Am I audible?
Yeah.
I am. Okay.
For the camera, that might require it to pick it up.
Okay. I'm not a software security professional. Is that a term we use? Well, a lot of the vocabulary is different here. I've probably given 500 conference presentations over the years, and I've never given one at a security conference. And I've noticed a few things about this conference, and it's kind of interesting. First of all, you guys are unnecessarily polite, I've noticed. I haven't heard any insults, any arguing or bickering. What, are you computer guys or what? Entirely too well-mannered. I come from C++, which is a very combative area. The other thing I've noticed is you're a lot of fun, strangely. I think it comes from consorting with criminals and trying to figure out the way evil people work. It just kind of makes you more lively. So it's a nice experience. And
we have a common threat.
it pulls you together, right? Yeah, my wife is a sociologist, and so I tend to look at things sociologically. Two stable models are the common threat development of community, which is one way to do it. The other way is normative distrust. If nobody trusts anybody else, you get a very stable society. C++ is the latter. But it keeps you on your toes. I was invited to work with Carnegie Mellon's Software Engineering Institute CERT effort because they were under the impression I knew something about C++, and they were in the process of developing secure coding rules. And rules are good, but they're not good in and of themselves. And I will be discussing a little bit about C++. I'd be happy to discuss as much detail about C++ as you like. But the trouble with C++ is that it's extremely complex. And when it's applied, when you use it, if you're not an expert, you can end up writing some very bad code very easily. The other thing is that C++ tends to be written in an idiomatic style. It's so complex that you can't write correct code unless you are familiar with the idioms. It's kind of like, I worked in Ireland for a short time, and ostensibly everybody's speaking English, except in the Aran Islands or something. But we're speaking different idioms, and I got into incredible difficulties in Irish pubs saying innocent things that turned out to be obscene in the local culture or something like that. And you can do the same thing in C++. You can write some very obscene code if you're not careful. So I will be talking a little bit later about automated checking of rules and idioms and how to analyze your source code in an idiomatic way. But first of all, probably some material that you people don't need. Why are we interested in software security and safety and so on? Well, I think it's pretty obvious. Anybody who's at this conference knows what's going on. When we talk about software security, though, we're not talking about security software, obviously. We're talking about the actual software that is laid open to attack, laid open to potential exploits. So what we're looking at in this situation is how do we actually get people to produce good, safe, secure software? Has anybody taught university here? No? So you haven't had the experience of teaching freshmen programming. First lab exercise, I always do the same thing. I give them a simple program, they have user input and so on, and then I usually schedule a lab session where everybody is there and we test everybody's program in front of everybody in the class. And the first thing I always do is sit on the keyboard. And if it passes that, then we actively try to break the program. I'm not so sure that people still do that anymore. Looking at some of the quality of the code that I've seen, people don't seem to be as careful as they were when I was a boy. I mean, when I was a boy, we had only 2 registers, and we were happy to have them. So people tend not to be, strangely, where security is even more important these days. A lot of people write applications like this. This is Robert Secord's favorite picture, apparently. And this is our typical application security right here. And this is our typical behavior in the presence of inadequate security. Great picture. OK, so again, we're going to be concentrating on poor software development quality. Okay. This was, at least last year, was considered the top threat. And certainly most of the exploits that we see relate to very simple programming errors. And once again, the more complex the language used to program, the more likely it is you can introduce inadvertently an idiomatically based error. You just violate the coding idioms, and well, that's, the game's up. So where does the insecurity come from? Complexity. Code is often inordinately complex, more complex than it has to be. A lot of people have their hands on the same piece of code. And of course, inadequate knowledge of secure coding practices. So yeah, and still most of our errors are very, very simple. Buffer overflows, cross-site scripting, injection, and things like that. These are things I learned about last month. As I said, I'm not a software security professional, but it still surprises me how simple these things are to prevent. Are there any C programmers here? C++ programmers? OK. In C++ nowadays, I give a talk where I encourage people not to use arrays, not to use if statements, not to use loops, and not to use pointers. Now, I'm overstating the case, but the point is, in modern programming languages, in a language like C++, you don't always have to use these low-level constructs. Buffer overflows just shouldn't occur anymore. You can write components that can't overflow and use them, and they're nearly as efficient as arrays. And so this is the kind of thing that we can look at automatically. This is a good quote. We wouldn't need so much, thoughtful security if we just had better software, if our developers are writing better software. So the CERT Secure Coding Initiative is still in its early stages. We have current standards for C and C++. When I say standard, it's a community-based standard. It is not yet an official standard yet, and it is still very basic and under development. As a matter of fact, in the future, we're going to have many, many, many more rules for both C and C++. C++ in particular is going to have, if they're going to have relatively complete coverage, there should be thousands of rules. Now, humans don't like to keep 1,000 rules in mind all the time when they're coding. So obviously, an automated check is a good idea. And so this is the goal of CERT, basically to make everything run slower, or alternatively, at least more correct or safer. OK, so one of the things in this talk, however, we'll see is that we can have much more security without actually making the software run slower. We can actually improve the speed of the software. A lot of modern design in C++ uses what's known as template metaprogramming, and that is doing at compile time a lot of processing that doesn't occur at runtime. So we can do things like one canonical example is if you're doing physical calculations on things like velocities and accelerations and so on. When you do those in university, right, you always do the algebra through on the units. So you don't end up adding a velocity to an acceleration or vice versa. You catch those errors there. In C++, it's very common now to use libraries that do that algebra at compile time to ensure the type safety of your result, and thereby, first of all, make your program more likely to be correct and safer, but also remove all those calculations from runtime. So a lot of these techniques actually make your code faster and smaller as well as safer. But again, when you're doing something like template metaprogramming, it's very complex, at least initially, and it's good to have some sort of automated check that can check the safety of what you're attempting. OK. So we are in the process. We just lost our funding. For the rest of the month, we'll be in the process of developing coding rules for C++ and C. Of course, the non-contract people will continue as best they can to work on these rules. And I'll try to contribute as I can gratis, because I do think they are important. And we basically partition up our advice into two sets. One are rules, and the others are recommendations. Okay, and the idea, of course, is to advance the state of practice, and my own interest is in education, as well as automated checking of compliance to the rules. My technical background is actually in an area called formal language theory, and when I discovered that that didn't pay anything, I went into compiler design. And it's turned out to be a very useful area, because compiler technology can be used in all kinds of ways, as we'll see, for checking any sort of aspect of software, both runtime and statically. Okay, so our overall thrust, again, just advance the state of the practice through community involvement. We recognize that we don't have all the answers, and so we open up our process to the public. We study what's gone wrong and then try to trace it back to the root causes of the problems, establish good practices, and finally educate developers. Robert Secord has a book out. I highly recommend it because he told me to recommend it. Secure Coding in C and C++. A very nice, good introduction for someone like myself to the issues of low-level security issues, buffer overflows, double deletion problems, etc., and how they can be exploited. My own, so I highly recommend having a look at it. My own work has in recent years been dealing with similar issues. Basically, here are common ways. These aren't necessarily security issues, but they're common problems that I see over and over again. And this is a way of communicating idioms to people programming in C++. When you write idiomatic code, you're less likely to make mistakes. When I say idiom, by the way, I'm talking about community, sociologically determined ways of programming, taking a complex language and reducing the complexity by having fixed ways, not fixed actually, but standard ways of combining these low-level features to produce a higher-level result. How do I copy one object to another? Sounds very simple, but it can be very, very complex in the presence of things like exceptions and in resource management and so on and so forth. And so now we know how to do that. We have an idiom for copy operations. The nice thing about idioms is they do change over time in response to changes in our environment. They're sociological constructs. Okay, so here's what we're up to. Secure coding standards, of course, for C and C++. We have a community development process, a wiki that we'll see late in a while. CMU offers training courses, Carnegie Mellon, and they are definitely practical courses. We're partnering with industry. We're also started up a partnership with software tool vendors. Fortify has stepped forward and agreed to work with us to develop automated verification and validation. And we're also working, as we'll see, with Lawrence Livermore Laboratory. They have a very nice tool that is, of course, free because it's government funded. And that's the one I've been working with mostly. Okay, we also have a course that's offered at Carnegie Mellon University. You can see which slides Robert Secord wrote because this is his course. You know, so this is all an ad. And if you want to have a look at it, you can get the slides right here. So interesting course, well worth your time. Particularly if you haven't been programming for a few years and you feel like getting back down and dirty with the rest of us and seeing what's actually happening and causing these exploits. Okay, and we are also in the process of developing training in addition for, rather than an undergraduate course as we have here, a course for software professionals. Okay, so this is all ongoing and subject to continued funding. The current work is actually funded by CERT, the Japanese national CERT organization, and that, as I said, is running out at the end of the month. So we're still looking for more funding. If anybody wants to step forward, feel free. Any government people here? You don't let them in, is that it? Okay. So right now we are looking only at C and C++ in the big way. Other languages are on the radar and will be covered later. We are also trying to hook up our efforts with the standardization committees for these two languages to give the the recommendations more a better likelihood of being accepted by the programming community at large. Okay, so here's a snapshot of our secure coding website. And you do have to get edit permission, but anybody can make comments. If you want to actually enter rules, you simply contact Robert. He'll make sure you're not a Java programmer or something, some other lower level species. And that was a C++ joke, kind of, except it wasn't funny. And you're a serious group. See, in a C++ conference at this point, several people would have already attacked me personally. So I'm not used to this politeness. I know, it's
Take you
bad.
aside later and
Paranoid.
I'm not paranoid yet.
paranoids have
Okay, development process is very straightforward. We solicit rules from the community. In my own case, I was submitting a few rules now and then I was actually hired on a temporary basis. We publish the rules, and then we have public vetting. We invite people to comment on it. We solicit comments from well-known practitioners, but hope to get comments from pretty much anybody. And then eventually, as the threads converge, this is a standard wiki development process, we move them into the secure coding standard when we get a consensus. And consensus actually is possible no matter what you've heard about C and C++ programmers. We actually do occasionally reach consensus on things. So very simple, straightforward development process. Now, we distinguish between rules and recommendations. Rules, very simply, are things that can cause a possible exploit, an entree for an exploit. You can actually specify exceptions in a small to the rule in a small number of cases, so that can be checked for. And most important, you can actually verify that the rule is being adhered to. It's very nice to say to have a guideline like code should be clear, code should be simple, but that can't be a rule because you can't verify that. Maybe if you could attach some statistics to it and verify the statistics. But rules basically are things that we can check. Things that are potentially damaging that can be checked and hopefully checked automatically. Here's an example of a rule. Obviously, free dynamically allocated memory exactly once. This is from the C part of the set of C rules. A well-known vulnerability, which I'm sure you can't read without opera glasses. And here we have an example, non-compliant code example. And I believe this came exactly from this particular issue. We have a double free situation here. If we have this error condition, we'll do a free, and then regardless of whether the error condition occurred or not, we'll do a free again. And this gives rise, of course, to a double deletion exploitability, depending, again, people are probably more familiar with this than I am, but depending on how your heap is managed by your particular language environment, this could cause arbitrary code to be executed. Here's a compliant solution, obviously. Don't do the double deletion. So this is, again, something that can be checked automatically if you have a powerful enough checker, or if you're willing to do a code review. This is the sort of thing that you can unambiguously say, this is in violation of the rule, because there is a potential for double free. This is not. There's no potential for double free. So again, this is a rule and a very simple rule. Some of the rules do get a bit more complex. Recommendations, it's more like good advice. The kind of stuff your mother would tell you before you left to program for the day or something. You know, don't make your code too complex. Don't hide inherited non-virtual functions. You know how your parents do it.
Strange libraries.
That's right. Don't call me strange libraries. Can I steal that?
Sure.
Yes. That's why I go to conferences. I get a good line or two every conference. Yeah, so these are, and the other issue is they may not necessarily be checkable in an automated way. So they often result the kind of good advice. So here's an example of a recommendation that's not a rule, because it's a little bit less specific and a little bit harder to check. Allocate and free memory in the same module at the same level of abstraction. That's a little bit more nuanced. But it's a good guideline because if you organize your code in this way, you can see, okay, I'm allocating this resource here, and I'm freeing it here at the same level of abstraction. It's very likely to avoid the situation we saw in the previous rule. So this is a much easier, a much softer recommendation. So here's an example of a non-compliant coding example. And here we have, at two different levels, we are doing a free here. We're also doing a free at a different level of, not of abstraction, but a different level of flow control. And this is, again, in violation of that recommendation. It's not necessarily erroneous code. Oh, this happens to be erroneous code. It is not necessarily erroneous, but it's a bad coding practice regardless. Okay, we're allocating our array of integers. We're passing the array. They might be freed, and they could be freed again, giving rise to the same problem. Now, again, we don't know if this is going to occur because it does depend, of course, on conditional code like this. But nevertheless, it's in violation of good coding practices. Okay, so here's our compliant solution. As your mother would say, just act like a person. Don't go freeing things at different levels of abstraction. Okay. So here's our goal. We want to put CERT out of business. I snuck this one in. Robert didn't see this. Again, this is an example incident report from CERT on just this particular violation. One thing I do need is a watch. But I presume that people just get up and walk out if I get too close to the end of this. Oh, good. All right, I do want to speed this up just a little bit. Here's an example of a distribution between rules and guidelines in C. I didn't have time to put one together for C++. But there tend to be more recommendations than rules simply because it's difficult to find something that the community will agree on is a hard and fast rule, because especially in C and C++, people tend to be opinionated, and they are often exceptional circumstances. I'm going to skip over this quickly so we can get to the remainder of the talk. The point is that we have a very kind of simple way of categorizing our rules and recommendations according to priority. And basically, very severe, easy to check, and likely problems have a very high priority. Difficult to check, less likely to cause severe problems, and unlikely events tend to have a lower priority. And that makes sense. But the actual computation of the severity level is kind of...
So high severity, highly costly is not your map.
well, you can have a high severity. Well, I'll go back. I wasn't going to do this. Here's our sophisticated algorithm. Ready? I didn't do this. We have a severity level, low, medium, high. Likelihood, how likely is this going to happen, and how hard is it to fix? I love this because usually people don't consider this. So if you have something that is of high severity, likely to occur, and easy to fix, that has a severity level of 27. In other words, there's no excuse for not fixing this right now. Typically, if you have a remediation cost of 3, that means you can write a little script or a program that will go through and fix it automatically. If you have to have a code review and have some intelligent, experienced person do the remediation, then there's a high cost. If you can have automatic identification but manual repair of something, that might have a remediation cost of 2. So the point is, it just gives us a ballpark estimate as to when we're categorizing these things, which of them should you attend to first? Obviously, the ones that are easy to fix and cause vulnerabilities are the ones you go for first. And that's what we're saying here. We try to hit the outside. So if you have a high severity, hard to fix problem, that is, you could have, well, let's say high, unlikely, and hard to fix. Then that's a severity of 3. So you just hope for the best. As I said, it's not a perfect categorization. I mean, clearly, we could fix that by having other levels of severity. But again, this is just a quick, off-the-cuff way of looking at something and deciding whether it's something you want to do right now or whether it can wait till after lunch. The identifier, to just very briefly, I'll skip over this, right? I'm not going to come back to this. Simply says this is a set of rules, file IO. Rule numbers are numbered, clearly. And then C stands for a rule, and A stands for a recommendation, advisory versus compulsory. And we have a very simple numbering scheme. So when you look on the website or on the wiki, you'll see a little summary of each rule. They give you this very likelihood remediation cost priority and level. And of course, this information is contained in this information, but this is just a convenience. And then we have this very simple naming scheme. And believe it or not, people will go around actually saying this: you violated FIO 30C. And people will know what you're talking about. After a while, it's, becomes a little in society thing.
So it doesn't encode the language it's for?
Well, implicitly it does, because you might actually find this same rule under C++ as it is in C, with a slightly different meaning. And that's something we are working on. This is the trouble with underfunded projects. People are trying always to do the most urgent, most severe things. And as a result, we often go in different directions. The other fellow who's on this, David Svoboda, is our C expert. And we try to talk as much as we can, or email as much as we can. He's in Pittsburgh, and I won't go there. But we do tend to get apart. We are trying to unify the standards as much as we can, but it's a lot of grunt work, and we just don't have time to do it. But eventually that will occur. Okay, here's what I want to talk about. How do we analyze these things automatically? A lot of times the testing industry focuses on dynamic analysis, which is essential. Unit testing, system testing, coverage analysis, profiling, profile-guided optimizations, and things like that. And this is all very useful stuff, and it tends to be emphasized. However, dynamic analysis is computationally complex. Just determining whether you've gone through all execution paths of a typical program is typically intractable. You just can't do it in a practical way. So it is, and it also tends to be very complex because you have the complexity of the code itself, the control paths, and of course the values of the data you're dealing with, all combined to make something of an incredibly difficult to analyze situation. Static analysis is looking at source code. There are also other static analysis that will take assembly code and analyze that statically, or object code and so on. But looking at static analysis of source code has a lot of advantages. You don't miss execution paths. You look at all the source. You do a complete coverage all the time, and you know that you've analyzed everything. It has no runtime cost, so you can analyze as much as you want. And as a programmer, you feel really calm because you know that nobody's going to complain about how slow your analysis program is, so you can write really bad code. No, you can expend the cycles to do a really good check. And we can also sometimes use our static analysis to eliminate a lot of runtime checks and actually make code perform a whole lot faster. And this is also, there's an old observation about optimization and correctness, and that there's a certain type of code that is maximally optimized, always bug-free, and trivial to maintain. And that's code that doesn't exist. And this is an old saw. It's been around. People have been saying that for 40 years and more. The nice thing about some static analysis is we can just get rid of a whole lot of code that we can determine cannot execute. And that code never causes any problems because it doesn't exist. So static analysis is very good in that way. We also tend to see that static analysis does catch more bugs than dynamic analysis. We need both of these things, but static analysis tends to be underused. So that's what we're going to concentrate on. And static analysis can check things that dynamic analysis really can't, like coding standards violations, or what I like to think of as unidiomatic code. Because by the time you get down to executable binary, all of your thought processes and design and idioms have disappeared, and you're left with this optimized bunch of bits. But it's very hard to reconstruct what the programmer was thinking or how the programmer was designing at that point. But static analysis is working with source code. If you have a very smart static analyzer, presumably you could even read comments, though I wouldn't trust any results like that. But the point is we can find whole classes of issues that are likely to be of interest. Coding standard violation, typos, portability issues. Even portability issues are hard to see at the bit level. And of course, security issues. We want to be able to look at these issues statically and actually flag the code that violates secure coding guidelines. We can also, now, we also know, of course, that at least at the present level of artificial intelligence, we can't have a program that really does a perfect analysis. We still need experienced programmers to look at our code. So how many experienced programmers with 10, 20 years experience is a typical organization going to allow to sit down and read code all day? Has anybody suffered through code reviews? They're essential. They're really good. They really find a lot of bugs. But it's and they have other good aspects too, like they cause employment. They cause you to hire consultants like myself, things like that. And they tend to train people. But finding bad code is usually a time-consuming process. You can read through a lot of good code before you hit bad code, or at least that's what we hope. The nice thing about static analysis is that it can focus your human resources in areas where it's going to be needed. And research shows that certain areas of code tend to foster bugs. Duplicated code. An interesting paper, I can't remember the authors, it's referenced in the back of the talk. Notice that when you have code like x equals 12 and then a few lines and then x equals 12 again. Now the compiler is going to see that and get rid of the second x equals 12. Just get rid of it. You're not going to find that in your binary code. And yet the presence of repeated code like that is a very good indication that there is a bug in that module. What's the reason for it? It's probably sociological. It's something that was been worked over by the same person and was not focused on very much, and therefore basically careless coding often results in careless code. And it's a good place to analyze. Complex code, obviously if code is very, very complex, that's a good place to look for bugs. So if you have triply nested loops inside of strange switches, maybe that's something you want to investigate. Inconsistent style. Different formatting styles in the same piece of code mean two different people with different worldviews have been munging the same code, and very often that leads to misunderstanding and bugs. And just plain bad code, and that's what I want to look at right now. Okay, so where does our insecure software come from? Well, a lot of it comes from complexity, incorrect or changing assumptions, and so on. But poor implementation of software interfaces and inadequate knowledge of secure coding practices. This is what we saw earlier, and these are areas that are very tractable by static analysis. These are things that static analysis can identify for us. So when I say static analysis, we have various ways of looking at that. Compiler errors, of course, and compiler warnings we should always pay attention to. But compilers, the job of the compiler is to try to translate your code, not translate your code. So compilers tend to be very forgiving. They'll warn you about things. But eventually, if they kvetch too much, then eventually people just turn off warnings, right? That's one way to get rid of warnings. Very fast. Code reviews are terrific. Code reviews have terrific results in finding software, but they're extraordinarily expensive. So static program analyzers really are the wave of what's coming. And I like to think static analyzers coupled with expert reviews, where the analyzers are guiding the reviewers and hopefully guiding during the review. Okay, so what we're going to be looking at is static analyzers in the context of our secure coding guidelines. Any threats or comments? Okay. All right, here is our favorite worm. I was looking at, this is a slide I got from Robert Secord, and he claimed the damage was 525 million. Microsoft itself estimates it at 2 billion for this one worm. And just as a little bit of history, we discovered the vulnerability. Security bulletin. CERT, a day late but accurate. Exploit. And so on. And then it starts spreading as usual. And finally, we've infected 1 million computers. So pretty, I don't know if this is considered a fast-moving worm, is it? Is this, I don't have a lot of experience in this area.
For 2003, it's pretty fast.
Yeah,
It's an old, slow
an old slow worm.
bounty.
Yeah, and the way it works is not all that important. What is important, I think, is what caused the exploit, what allowed the exploit. And this is code that is depressingly common. I don't know why people write code like this. They should know better. An unbounded string copy. This is code written in this kind of kindergarten code. The world's good, nobody will give me a big array, you know, whatever. Everything's fine. And this little loop here is what was exploited. It was just standard buffer overflow problem. All right, so I can complain about, you know, how programmers aren't as good as we used to be when I was a boy and so on. But I think another thing that's telling about this piece of code, now if you're not a C programmer, this doesn't look very pretty. I promise you that this actually looks somewhat normal. After you've been programming in C for a while, it looks fine. It's like hitting yourself with a hammer, you know, in the head. After a while, it's not so bad. So this is normal-looking C code. But as an old professor, I look at this code. Hey. That was supposed to be more exciting than that. I don't know. These were supposed to come in one at a time and as the tension built. Looking at this code, there's a whole lot going on here in addition to the actual bad code. For instance, now we have one C programmer here, right? This probably won't be very exciting then. If you're a C programmer, this is the ultimate in excitement. As it turns out, this array bound, I'm passing a couple of arguments to this function. This array bound is ignored in C. It does not play any role in the semantics of this function. It's totally ignored. So when I see that, I think, okay, whoever wrote this, whatever his or her good qualities are, being a C programmer with some experience is not one of them, because this is a lie, a patent lie. It's simply ignored. So I'm actually passing a pointer, not an array of a certain length, is what's happening. Maybe a Fortran. Well, Fortran programmers, this is actually it's a very good point. Especially there are particular problems with C++ programmers programming Java and Java programmers programming C++, because the languages look similar. But they have totally different sets of idioms for correct programming. And you find Java programmers writing absolutely terrible C++ code and vice versa. Okay, so I'll just, in brief, there are a whole lot of problems here. This person would not have passed my freshman programming course. Global variables, bad. Global variable, bad. A magic number. Why 2? What does 2 mean? Well, 2 characters. 2, is it a wide character? So is it 1 character? What does it mean? So this is just not done. And again, we tend not to write loops like this. We prefer to use a library function for 2 reasons. 1, it's more likely to be correct, and 2, it's liable to be a whole lot faster. So this is just bad code. So the point is, we can find things like this, even if we can't detect the actual exploit. Just running some automated check on this code would have identified so many bad programming practices in such a small area. This would be guaranteed to be looked at, and any human reader who's an experienced C programmer will immediately see this. This is a red flag. If they're told to look at this function, they will find this. There's no way they can't. Okay, so we could have saved $2 billion. Okay, so we looked at a couple of tools. Fortify is a commercial product, and I'm not that familiar with it. I didn't work with it. But we decided to use a commercial product, and we have to thank Fortify for stepping up to the plate and actually donating their time and software to the effort. And we also worked with a research project from Lawrence Livermore, which is more of a compiler-based analysis tool. And so I was working on that, given my background. Fortify first, just in brief, we were looking at which of the C secure coding rules could be handled by Fortify. A certain number of them could not be implemented. could not be checked automatically by Fortify due to the way Fortify analyzes programs. Typically, it throws away some information during pre-processing and so on. So certain things can't be checked. We were able to, in a very short time, this is over a course of a month, I think, 1 or 2 people implemented quite a few of these rules. 113 and 180 rules for the C language were implemented in relatively short order. So for very little staff time produces a result that could find a whole lot of bugs really fast. And of course, finding bugs in source code is much preferable than finding them after you've released the code. What is it, 3 orders of magnitude in cost difference to find it, for the programmer to find it before it goes to test versus fixing it after the fact? I didn't exactly make that number up, but it's some large order of magnitude difference in cost. Might be 5, I don't know. C++ rules in Fortify, a little further behind there, 63 out of 99, but still a pretty good coverage of this rule set. And keep in mind that these are automatically checked rules. Okay, so if you want to see the exact rules that have been implemented in Fortify, here are a couple of links for you. Okay, and again, just briefly, Fortify has a number of different engines that help you to analyze your code, which is all very interesting, but I want to get on to. Yeah, JP CERT, the Japanese National CERT Organization, which is a separate organization from CERT, they just have the same name, funded the study, and we actually did analyze 3 different projects, and including this karaoke device, which I thought was very exciting. Okay, but okay, on to Rose. This project actually is a compiler-like thing. It actually uses the Edison Design Group C++ compiler front end, which is a very fine, correct compiler front end used in a number of industry compilers. And it does a very detailed analysis of the source code. It maintains things like, even down to the level of formatting, preprocessor things, and so on, where comments occurred. Very, very rich in information. And that's especially important for static analysis because very often, as I alluded to earlier, you may anecdotally observe that programs that are formatted inconsistently tend to have a lot of bugs associated with them. Now, whether somebody indents 2 spaces or 4 spaces doesn't seem to be very important with respect to correctness. But as a pointer to code that is likely to harbor an exploitable bug, that's a good sign. If people don't care about their formatting, or if different people are munging together on the same code, that's a flag. That's something to look at. And so that level of information turns out to be important. So it does produce an abstract syntax tree, which we can then use for static analysis. And there is additional information coming online. There's a good flow control analyzer coming along that'll be very, very handy for checking a certain class of problems in C++ with respect to exception safety, a very hard thing. But here's a very simple example. First of all you old computer science professors, if your student gave you this code, what would you say? Magic number. This is what Scott Myers, a C++ expert, calls the keyhole problem. They're expecting everything to be less than 256 bytes. Now, in C++, this is just bad code. We would not use a buffer, a fixed-size buffer like this. We would have a smarter object that could efficiently hold 256 bytes, but then would extend itself automatically as needed in extreme situations. I actually was, I don't know why this occurs in government code so much. I was looking at some satellite code that was government funded, and I saw a buffer that had 17,463 bytes in it, I think it was. Now, how did they get that number? Oh, it broke again. Okay, let's just keep extending it. But the point is, you don't want it to break ever. You want it to be efficient, but you want it to not break. So the point is, this is just bad code. And once again, if you're just looking at code quality, you'll find this. You'll find the use of this, what we call a magic number, and then have a look at it. And then you'll gasp in horror when you see it's not working. When you see that we are copying a potentially large string into a fixed size buffer with no check. So this is a standard buffer overflow vulnerability. Yes?
Why would you even bother with the string copy there? Why wouldn't you just have jar star buffer equals A and B?
Because as it turns out in C and C++, that wouldn't compile. Should it compile? Probably. Does it? No. So yeah, we're a little low level, but we like it that way.
This is an extremely common idiom that I see in CVE once a week at least.
Yeah. When you say idiom, a kind of anti-idiom, or
Anti-idiom.
I don't even know if that
No,
makes sense.
It's an idiom, it's not a good one.
Yeah. Well, it's done. Typically, idioms do it, so you got to be careful. That was also a joke, but not funny either. This is just to be avoided now. And in C, we can certainly do a stern copy instead of a stir copy, or some reasonable thing. But this is distressingly common. People will say, well, who would have an environment variable bigger than 256 bytes? A hacker, idiot. It's like there are bad people out there. So anyway, so this does actually violate the rules, the C rules, stir 31C. And guarantee storage for strings has sufficient space for the character data and the null terminator. And getenv makes no promise about the size of the string it returns. And so obviously this is a very easily exploitable thing. All you have to do is have a command line access to this program, and you're free. You can do all kinds of stuff. So here my colleague David Svoboda has put together some very pretty graphs. I'm sorry to say that my PowerPoint isn't working the way it should. Everything's supposed to be animated, but I guess that's what I get for using Windows 2000 on this thing. I don't know if I should blame Windows or whatever, but this behaves differently on my other machines. In any case, Rose will build us this abstract syntax tree.
Variable turn on animation.
Is it? You think so? I don't know. I tend to stay away from too close familiarity to, never mind. I don't want to get sued. So we build an abstract syntax tree, and again, the animation's a little bit lacking here. But nevertheless, the important point, since I'm about to run over, I have run over, is that it builds an abstract oh, look at that. It animated. And we're able to analyze our code and actually check this with a very simple checker, which I will show you. Stir31C can be checked with this very simple piece of code. And I simply examine, am I doing a stir copy? If so, let's look at the first argument. Is it a fixed-sized array? Very simple. That'll catch most of these. It's not perfect. We can still have a pointer to a fixed-sized array that this checker will not catch. But this is going to catch almost all of those exploits. And it took David, probably knowing his coding skill, upwards of 12 seconds to write this. And testing it probably took another 2 minutes. And that's going to catch, well, it would have saved $2 billion for somebody, apparently. Now,
that actually would create a ton of false positives.
It can.
Programmers tend to copy little literals into large buffers all the time.
Yeah, and again, some of the rules, especially when we got to C++, we had checkers that caught almost all of the violations, but also issued a lot of false positives, so those are not included in what you're about to see. So you can actually, we run a lot on real code to catch the false positives. But yeah, some of the rules are considerably longer than this, of course, and a lot of that has to do with not annoying people to the extent where they'll, as with compiler warnings, stop checking.
Have you guys worked with Clarity or Clockwork or any of the major static analysis vendors yet?
I believe there has been some work. I have not been involved in it, so I'm not sure to what level. We did talk to actually 2 or 3 commercial vendors in addition to Lawrence Livermore, and we ended up working with Fortify for I don't know what the reasons were. It might have just been practical, or they were ready faster, and we saw our timeline coming to a conclusion. Yeah, false positives are always a difficult issue with compiler warnings as well as with a static analysis tool like this. Okay, so we're not as far along with rows in C. Now, when we're checking C++, things kick up an order of magnitude with more complexity. We have a lot of standard library issues. The standard libraries have certain, they all have certain idiomatic ways they have to be used. If anybody's familiar with the standard template library, you'll note that it's basically a collection of conventions about how to use it properly. Very easy to write bad code using the standard template library in C++. We also have operator overloading, hierarchy design issues for hierarchies of types, template metaprogramming issues, things that execute at compile time and don't appear in runtime code, and exceptions. So we have a whole lot more complexities to check. Some of the recommendations are quite simple, like don't overload the comma operator in C++. You're allowed to take existing operators and give them new meanings. Overloading the comma operator, however, tends to result in difficult to understand code for reasons that I will go on at great length after class if anybody wants to hear about it. Checking something like that's very simple. Here's some of my code. You notice the nice indentation and so on. And very simply, it looks for a function declaration and asks, well, is the name of this function operator comma? If so, issue a diagnostic. Okay, very, very simple rule. A little more complex, do not hide inherited non-virtual member functions. This is kind of a standard recommendation for type hierarchy design in C++. And if you violate it, you basically break polymorphism. You have an object, and sometimes you manipulate it with one interface, sometimes another interface, but you want the same behavior in either case. Otherwise, you get a very complex situation. If you hide an inherited non-virtual member function, you break polymorphism, and the same object will behave differently depending on which interface you use to manipulate it. So, well, notice.
Anything do you care about that? This is practical. These are just bottom-up rules from a language point of view, but nobody's
Yep.
really attacking this.
Yeah,
We have some C++-ish kinds of things in CWE, so in our classification of different weakness types. This one, I don't remember if we have this one in particular or not. But in CVE of publicly reported vulnerabilities and publicly available software, we rarely have a level of insight.
Yeah, we don't
into
know
something
what
like this.
caused it at this level.
yeah. Now keep in mind, this is a recommendation, and here's the check for it. Let's look at a rule. And here, this one looks a little obscure, and this could result in a vulnerability. Avoid calling your own virtual functions and constructors and destructors. In other words, don't treat yourself as a polymorphic object while you're being created. And what can happen here is you can actually get, well, you can get a core dump, or you can also end up calling, it's actually undefined behavior, which means you might call a function that doesn't exist, or a function that is supposed to dump core but may have been overwritten. So this could give rise to a vulnerability. I haven't developed that sneaky mindset yet that tells me.
Tools that you're working with, these static analysis tools, follow multiple code paths that may lead to this. Call one member function, call
That's
another,
what-
then instruct, and then calls virtual function.
Not yet. I believe Lawrence Livermore is just completing their flow analysis graph, and that's going to go along. Then I'll have the abstract syntax tree and the flow analysis that I can layer on top of each other, and then I can do that. My own particular, yes, the answer is yes. It's certainly doable.
I mean, I've worked with static analysis tools for the past 4 years.
Yeah.
A lot of commercial, none of them will go to the nth degree to find this stuff. But they can.
Yeah,
Some
this-
will quit after trying to call, 10 procedural calls.
I think the reason that Rose does so well in this is because it's not just a static analysis tool for analyzing, looking for faults in software. It's actually a static analysis tool they're using for all kinds of things, including source-to-source translations. A lot of these people are interested in doing very fast numeric processing. And so they'll take a program, analyze it to death, and they're starting to do the flow analysis, and actually take your source code and rewrite it from C++ to C++, but in a more efficient way. And so for that level of optimization, they actually need a ton of information, and they have to basically have unbounded analysis up until resource exhaustion. So yeah, we should be able to overlay that path flow analysis with our static analysis.
To kind of build on that, we actually found that we were able to do a lot to reduce our false positive rate by doing a high degree of interprocedural analysis, following data and control flow log. And on the flip side, there are certain classes of problems that are really only findable when you're doing that kind of whole program data and control flow analysis.
Yeah.
Because, I mean, things like tainted data from user sources going into things like databases and such. Those kinds of things depend heavily on control flow, especially if you have validators in some of your control flow paths, but not all of them.
Right.
So.
Yeah, and again, this is early days. I'm very excited by the capabilities of the ROSE tool, and we're just getting our feet wet with it. And as more capability comes online, we're going to be doing more and better analysis. And the false positive issue is an important one, and we're trying to avoid. I'll skip over the code. Here's a subtle rule by Dan Sachs, another well-known C++ expert. A variadic function, a function that has a ... and ellipsis argument list, is a function to which you can pass anything at all. If it sounds unsafe, you're right. In C++, however, we use these functions all the time in template metaprogramming. So we declare them, but we don't execute them at runtime. We execute them essentially at compile time in order to do optimizations, in order to uncover static information about the program. So the rule is a little bit funny. You can have variadic functions, you just can't define them. You can declare them and use them for metaprogramming purposes, but you can't define them. So the point is, some of these rules are a little subtle, and that's one reason why we have so much community input, because if you're just coming into this area without having 10 or 20 years experience in it, you will not realize the value of this seemingly dangerous function. So in short, key points. Static analysis, especially in the context of checking secure coding rules, does seem to be a very important and wave of the future as far as avoiding exploitable code and so on. And basically, because we can automate it, and because it does so well in directing our human resources, we actually may possibly be able to analyze and check all of our code before we release it, something that's not happening today. I'll take any questions after we're finished. For more information, go bother Robert. That's his job. And then feel free to contact me or Robert at any time. Thanks very much. Anybody want to discuss metaprogramming?
Please take a feedback form on your way out. Run back here in the chair. Lunch is in the vendor exhibit area. So hurry down because everybody else got 2 minutes.
Thank you.
So you're trying to learn how bad guys think. Have you familiar with CWE at all?
No,
Yeah, where's the? Do we have a mapping, a master mapping?
I've been trying to, before coming here, of course, I got nervous. I thought you guys would be less polite than you are. And so I was trying to learn all these